Hey everyone, and welcome back to another explainer. Today, we're taking a really fascinating trip that goes straight from the macro to the micro. We're going to deconstruct the materials that make up our everyday world, looking at the fundamental physical differences between metals and nonmetals, and then we're going to zoom way in to understand the invisible forces that actually bind them together. Here's our roadmap for today. First, the physical divide, then the chemical rule breakers, trial by fire and water, the reactivity hierarchy, and finally, the ionic bond. Let's jump right in. I actually want to start with a really quick exercise. Just take a look around your room right now. Glance at the objects sitting on your desk or your walls. Can you mentally separate everything you see into just two simple categories, metals and nonmetals? It sounds pretty intuitive, right? Your laptop casing, the window frame, maybe a desk lamp. This little mental exercise is going to kick off our detective arc today as we start categorizing our world based purely on observable physical traits.
Section 1. The physical divide. What we can see, touch, and hear. Let's start with malleability. By definition, this is the ability of a substance to be beaten into thin sheets. If you took a hammer and smashed a piece of coal, which is a nonmetal, it would just completely shatter, right? But metals are generally hard and can take a serious beating. What's cool is how this explains the real world around us. Gold and silver are actually the most malleable metals in existence, and that is exactly why we can craft them into incredibly delicate, paper-thin pieces of jewelry without them just snapping in half. And that leads right into our next property, which is ductility. This is the ability of metals to be drawn into thin wires. It's super closely related to malleability, but instead of flattening the material out, you're stretching it. And honestly, there is a totally mind-blowing fact about this that I have to share. Get this. A wire 2 kilometers long can be drawn from just 1 single gram of gold. Seriously, imagine holding a piece of gold the size of a tiny little pebble and being able to stretch it across an entire neighborhood. It's because of this extreme malleability and ductility that we can actually mold metals into all the wildly different shapes we rely on every single day. Next up, we have sonority. This is simply the property of producing a ringing sound when a material strikes a hard surface. Think about it. If you drop a wooden block on the floor, it just thuds. But if you drop a metal spoon, it clatters and rings. This is exactly why school bells, or honestly any bells at all, are crafted from metals. They are inherently sonorous. Finally, to wrap up our physical divide, we have conductivity. Metals are fantastic conductors of both heat and electricity. The absolute best conductors of heat are actually silver and copper, which perfectly explains why copper is constantly used in cooking vessels. But there is a flip side here. Because they conduct electricity so well, the wires carrying current into our homes need a serious safety barrier. That's why those electrical wires are coated in a nonmetal, like a rubber like PVC, to keep that current safely contained so we don't get shocked. So right now we have a really neat, tidy set of rules for metals based on these physical properties. But as you probably know, chemistry is rarely that simple. Section 2. The chemical rule breakers. The exceptions to the rules. So we established earlier that metals are generally hard solids. Well, look at this comparison. All metals exist as solids at room temperature, except for mercury, which is completely liquid. And it gets weirder. Metals like gallium and cesium have such incredibly low melting points that if you were to just hold them in the palm of your hand, your own body heat would cause them to melt into a liquid puddle. And the rule breaking definitely doesn't stop there. We generally accept that metals are hard and nonmetals are soft or brittle, except the alkali metals, things like lithium, sodium, and potassium, they are so incredibly soft that you can literally slice right through them with a regular butter knife. Meanwhile, over on the nonmetal side, we have carbon. In one of its forms, carbon becomes diamond, which is absolutely not soft. In fact, it is the hardest natural substance currently known to humanity. So clearly, physical properties alone just aren't going to cut it when we classify elements. We have to look at how they react, zooming in to see how these materials behave under chemical stress, specifically when they're exposed to oxygen and water. Section 3. Trial by fire and water. Escalating reactions. Let's look at exactly what happens when metals are burnt in the air and react with oxygen. There is a very clear escalation happening here. Down at the bottom, we have gold and silver. They do absolutely nothing, no reaction at all, even at extreme super high temperatures. Moving up a bit, solid iron won't burn, but if you sprinkle iron filings over a flame, they will burn vigorously. Then there's aluminum, which reacts by forming a protective oxide layer. We actually take advantage of this industrially through a process called anodizing to make it resistant to corrosion. But then, at the very top of our escalation, we have sodium and potassium, which produce extremely violent reactions. The crucial takeaway here is just how extreme this reactivity can get. Our source material notes, metals such as potassium and sodium react so vigorously that they catch fire if kept in the open. Seriously, just to protect them and to prevent accidental fires in the lab, these metals literally have to be kept completely submerged in a jar of kerosene oil. They are just that desperate to react with the everyday moisture and oxygen in the air around us.
But what about the metals that don't react easily? We just said gold is incredibly unreactive, right? Well, chemists found a workaround. Enter aqua regia. That's Latin for royal water. It is a freshly prepared 3-to-1 mixture of concentrated hydrochloric and nitric acid. Now, neither of these acids can dissolve gold on their own. No way. But mix them together, and this fuming, highly corrosive liquid becomes one of the very few reagents on Earth capable of fully dissolving gold and platinum. So there are massive, fundamental differences in how these elements behave. And to make sense of it all, scientists created a specific hierarchy to help organize the chaos.
Section 4. The reactivity hierarchy. Organizing the chaos. By observing what we call displacement reactions, which is where a more reactive metal will literally kick a less reactive metal out of its own compound solution, we've been able to build this amazing visual cheat sheet, the reactivity series. Up at the top, we have our most reactive metals, like potassium and sodium. Right in the middle are our everyday structural metals, magnesium, aluminum, zinc, and iron. And then safely down at the bottom are the least reactive metals, like copper, silver, and gold. This hierarchy dictates exactly how a metal is going to behave out in the wild. But why? Why do some metals react violently while others just sit there and do nothing? To answer that, we have to zoom right past the physical traits, past the chemical reactions, straight down into the invisible subatomic world.
Section 5. The ionic bond. Zooming into the subatomic.
The underlying motivation of the entire chemical universe is so fascinating. Why do these metals react in the first place? Well, the ultimate goal for every single atom is to attain a completely filled valence electron shell. They just want to be perfectly stable and unreactive, exactly like the noble gases. Generally speaking, metals have a few extra electrons that they desperately want to get rid of, while nonmetals are out there actively hunting for extra electrons to complete their own shells.
So let's look at how this plays out step by step with the formation of something you eat every day. Ordinary table salt, or sodium chloride. Step 1. Our highly reactive metal, sodium, has one pesky outer electron. It loses that electron and becomes a positively charged cation. Step 2. Our nonmetal, chlorine, needs exactly one electron to complete its shell. It happily scoops up that electron, becoming a negatively charged anion. Step 3. We now have a positive ion and a negative ion, and opposites attract. Strong electrostatic forces instantly lock them together to form NaCl. They don't just float around as isolated molecules. They exist as an aggregate of oppositely charged ions bonded super tightly together. Because these ionic bonds, which are formed by that pure transfer of electrons, are just so incredibly strong, they end up creating materials with very specific macro properties, which brings this whole explainer full circle. Ionic compounds, like salt, are solid and hard precisely because of that strong electrostatic attraction. But unlike the metals we talked about earlier, they are brittle. They will absolutely shatter under pressure. Because the bonds are so tight, they require massive amounts of heat energy to break apart, which means they have extremely high melting and boiling points. And interestingly enough, while they generally dissolve super easily in water, they are completely insoluble in solvents like petrol or kerosene. So we've traveled all the way from the physical traits of the metal casing on your smartphone, straight down to the electrostatic forces locking its atoms together. I want to leave you with this provocative thought. If everything you see, feel, and use on a daily basis is really just a different combination of electrons shifting between elements in an endless quest for stability, what chemical reaction are you physically touching right now? Keep observing the world around you, because the invisible rules of chemistry are quite literally holding it all together. Thanks for joining me on this one, and I'll see you in the next explainer.